Hello everyone. So in this video we are going to solve the assignment 6. So we have seen the common source amplifier. Now we are going to solve an assignment. Okay, so let's see the questions. This is the first question. You can solve it on your own, then you can watch the solution. This is the first question. I will show you all the questions. This is the second one. This was the second question and these were the questions. These were the information given and these were the questions. And, this is the third one. Fourth. Okay, that's it. No other question is there. If there is anything that I missed, this I missed, I guess. Yeah, this is one more question. So you can see all the questions now. Now I will give the solution of all the questions one by one. So let's start solving the first question. So mu n c x w by L value is given, Vt value is given, and it is given that lambda is 0. They are saying that small signal model is drawn. So this is the small signal model. Small signal model means AC analysis. So AC model they have drawn already. There is no VDD bias, there is nothing like that. It is present there, but it is not shown in this model. VDD is present here. There is certainly VDD present. Here there is certainly VGG present. So they are present, but they are not being shown because they have only drawn the small signal model. Now they are saying that the gain magnitude is 8. Gain magnitude is 8. So what is the gain of this circuit? This is a common source amplifier. What is the gain? Simply minus GM RL, right? You know this thing. And the magnitude is given, that is equals to 8. You need to determine the bias current. What do you mean by bias current? DC current. You need to determine the DC current. Now you will say, sir, we need to determine the DC current. So I have to do the DC analysis. And for doing the DC analysis, I need to know the VDD value, VGG value. No, it's not necessary that you need to do the DC analysis. By observing the data, you can find the DC current as well. Let's check that out. Minus GMRL is given, that is equals to 8. So from here, what you can determine? GM into RL is 50 kilo ohm. That is equals to 8. So GM value is 8 by 50k. What is 8 by 50k? Where is the calculator? 8 by 50. 8 by 50k is 0.16 millisiemens. So this is the value of GM we are getting. This is our GM. Now you know the formula of GM. There are three formulas of GM. Mu n x w by L VGS minus VT. Is that of any use? No, because you need to determine the IDC value. You need to determine IDC value. So that is of no use. The second formula is 2 IDC upon VGS minus VT. The second formula is 2 IDC upon VGS minus VT. So here you need to determine IDC. Okay, that is fine. But do you know the value of VGS minus VT? You know the value of VT, but you don't know the value of VGS. So this is also of no use. What is the next formula? The next formula is GM equals to root 2 mu n cox w by L ID. This is the formula, right? So you know the value of mu n cox w by L. You know the value of mu n cox w by L, and IDC you need to find. And GM value you also know, that is 0.16 millisiemens. From here you can find out the value. So root 2 mu n cox w by L is 100 micro into IDC. That would be equals to 16 into 10 to the power minus 5, right? 16 into 10 to the power minus 5. So it would be 2 into 10 to the power minus 4 into IDC is equals to 256 into 10 to the power minus 10. So IDC here would be 256 by 2 would be 128, and this would be 10 to the power minus 6. So IDC would be 128 microampere. Sometimes calculation becomes a problem in these kind of questions, but here I am showing you every single step of calculation as well, so that you don't mess it up in the examination. So this is how you solve these kind of problems. Just don't get into complex calculations. This is just 0.16 milli, so I wrote 16 into 10 to the power minus 5. Then square will come here, 256 into 10 to the power minus 10. Then IDC would become 128 microampere. This is our final answer. This is a very simple question. Just I picked this question so that you shouldn't think that if if I have to calculate a DC parameter, I have to do the DC analysis. No, it's not necessary. Without doing the DC analysis as well, you can find the DC parameter, right? Let's move on to the next question. So this is a big question. There are three questions involved in this one. So the given scenario is mu n Cux W by L value is given, Vt value is given, the same value is, and transistor is biased at 128 microampere. It is biased at this current only, which we calculated. So it is biased at 128 microampere current. At operating point, your VDS is equals to VGS plus 1. This is your VDS. VDS is equals to VGS plus 1 at operating point. And the bias current flowing through R12 is 10 microampere. What do you mean by bias current? That means DC current. DC current flowing through R1 and R2 is 10 microampere. So you have to determine the VDD value, you have to determine R1, R2 value, and you have to determine small signal voltage gain. So first we need to determine the VDD value. So let's just do the DC analysis first. You have to use the given data smartly. So we are doing the DC analysis first. So while doing the DC analysis, capacitors will be open circuited. This is R1, this is R2. Then there is this MOS, this is grounded. Then there is this RD. VDD is also there. And this is also VDD. You need to determine the value of VDD only. The bias current is, there will be no current here. There will be 0 ampere current here. And the bias current is 128 microampere. This is given. This current is 120. No, sorry. This current is 10 microampere. Sorry. The bias current flowing through R1 and R2 is 10 microampere. So this current is 10 microampere. And this current is 128 microampere. And RD value is given, that is 50 kilo ohm only. This is 50 kilo ohm. So this capacitor is open circuited, this capacitor is also open circuited, right? Only this much circuit is there, this much circuit, right? So you need to calculate the VDD value. What is given? Given is VDS equals to VGS plus 1. What is your VO drive? VO drive is VGS minus VT. VGS minus VT, that would be equals to VGS minus 1, right? So here VDS is greater than V overdrive. That means it is working in saturation region. That's for sure. So it is working in saturation region. Tell me, what is the value of VDS now? In this circuit, what is the value of VDS? VDS is, this is VDS. VDS is VDD minus ID into RD. VDS is VDD minus ID into RD. Are you agreeing with this point? Because this is drain. So VDD minus ID into RD. So 50 kilo ohm into 128 micro. 12 6.4 it would be. So VDS would be VDD minus 6.4. This would be your VDS. This is equation 1, I can tell. This is our VDS. Because I am going to use this one. This is given. This thing is given. This is given. I am going to use this one. Now, do you know the value of VGS? No, you don't know the value of VGS. But you know one thing, that is the current is 128 microampere. What is given? Given, that is ID is 128 microampere. This is given. You know the formula of ID, that is mu n Cux W by 12 VGS minus VT whole square. That is equals to 128 microampere. Mu n Cux W by L value is 100 micro by 2. VGS minus VT value is 1. That is equals to 128 micro. So 2 point here, what will happen? Mu n Cux W by L is 100 micro only, no? Yeah. So what will happen? 2.56 it would be. So VGS minus 1 would be this, and this will get cancelled. This is 50. This is 256. 256 by 100 would be 2.56. And under root of this. What is the under root of 2.56? It is 1.6. So VGS would be 2.6. So your VGS value is 2.6 volt. And what is given? This is the equation 2. It is given that VDS is equal to VGS plus 1. It is given. And you know what is VDS? VDS you calculated VDD minus 6.4. What is the VGS value you are getting? 2.6 plus 1. So VDD value will be 10 volt. That's it. This is the final answer. So how did I thought of it? Look, if I need to determine VDD value, that means I have to consider VDD in my equations. I need to take VDD action. I need to take VDD in action. तो मैंने VDD को एक्शन में ले लिया. कैसे लिया? How did I take it in action? I determined the value of VDS. VDS is VDD minus ID into RD. So VDD minus 6.4. Now to use this equation, I need to determine the value of VGS. For that, I have the current 128 microampere. So I determined the value of VGS. VGS is 2.6 volt, and then I calculated this value. Well and good. Now I need to calculate R1 and R2. For that, I will use this much thing. So I need to calculate R1 and R2. I have the value of VDD. VDD is 10. So let's calculate the value of R1 and R2. So what is given? What is given? Given that VDD by R1 plus R2 is equals to 10 microampere. Are you agreeing to this point? VDD by R1 plus R2, this current VDD by R1 plus R2 is equals to 10 microampere. What is the value of VDD? VDD is 10 microampere. Sorry, VDD is 10 volt. VDD is 10 volt. So 10 by R1 plus R2 is equals to 10 microampere. So R1 plus R2 is 1 mega ohm. This is your R1 plus R2. Now, how do I get another equation? Because there are two variables, R1 and R2, two variables are there. So I need to determine one more equation. So how do I get that? I know one thing, that my VGS value is, I know one thing, that is my VGS value is 2.6. And here what is the VGS value? VGS value is 10 micro into R2. Say yes or no. This potential is equals to VGS only. So 10 micro into R2 is equals to VGS. Here VGS is equals to 10 micro into R2, and that is equals to 2.6. So here what will be the value of R2? That would be 260 kilo ohm, right? Because 10 would come here, this would make 0.26. 0.26 into 10 to the power 6. So 260 kilo. R2 would be 260 kilo. So this is one of the answer. And if R2 is 260 kilo ohm, then what will be the, what is 1 mega ohm? You know this thing. What is 1 mega ohm? 1 mega ohm is 1000 kilo ohm. This is 10 to the power 6. So it would be 1000 into 10 to the power 3. So what will be the value of R1? That would be 740 kilo ohm. Right? So we have calculated the value of R1 and R2 as well. Very easy, very simple. Just you need to think in the examination very quickly. If a lot of data is given, you need to think in the examination which data is useful for me. So how you will get that? By the practice. That's why we are solving the question. If we solve more and more question, we will be more comfortable with these kind of analysis. Right? I am also telling you how I am thinking the problem. Now the next question is, you need to determine the small signal voltage gain, which is very easy. So how will you determine small signal voltage gain? I guess I can copy this circuit. We will be changing it, but let's just copy it for once. So you need to determine small signal voltage gain. For determining the small signal voltage gain, this biasing we have already seen in the previous lecture, right? So for determining the small signal voltage gain, what we will do? These will be shorted. We are having all the values of R1 and R2 as well. R1 was 740, and R2 was 260. What will happen to this? This will be, arey yaar, this will be shorted. Now both this R1 and R2 will come in parallel, because from here to ground you are having, from this potential to ground you are having 740, from this potential to ground you are having 260. So both will come in parallel, right? And this will also be open circuited. So this 50 and 50 will also come in parallel, because from V0 to ground you are having 50 kilo ohm, from V0 to ground you are having 50 kilo ohm. So what will be our final circuit? Let's draw our final circuit. That would be 100 kilo ohm. Then these two will come in parallel, that is 260 kilo ohm parallel with 740. This we will be having some answer. Then we are having the MOS, and from V0 to ground, V0 to ground 50 kilo ohm, from V0 to ground 50 kilo ohm. Fifty kilo ohm parallel with 50 kilo ohm would be 25 kilo ohm. So what will be the gain? What did I tell you? First write the potential here. Then this potential will be amplified with GM factor. Write down the potential here. This potential will be amplified with GM factor and will be flowing through this resistance. Right? So you can write down your gain. If you have seen the previous lecture, it will be a cakewalk for you to write the gain. First, determine this potential, V potential, then this will be amplified with the GM factor. The current flowing will be GMV, and that will be flowing through the resistance. So this current would be GMV. So first we need to determine this factor. So 260 kilo ohm parallel with 740. So 260 into 740, that would be 192.4. 192.4 kilo ohm. So what will be this potential? 192.4 kilo ohm. 192.4 divided by 292.4. So this potential will be 0.66, 0.658 you can say, of Vs. So V is 0.658 of Vs. So what will be your V naught? So V naught will be minus Gm into RL. RL is load is 25 kilo into this V potential. V potential is 0.658 into Vs. So you have all the values, but you don't know the value of Gm, right? So how we can calculate the value of Gm? Because we have all the data, so certainly we can calculate the value of Gm as well. So Gm, how do we calculate Gm? Since I know the value of Vgs minus Vt as well, I know the all values from, I have multiple formulas. So from anywhere I can calculate the value. The simplest formula I find is 2 IDC upon Vgs minus Vt. So I guess I will apply this formula only. So 2 into IDC, what was the IDC? 128 microampere. What was the VGS value? It was 2.6 as far as I remember. VGS value was 2.6. Here you can apply all the three formulas, because you also have the value of mu n Cx W by L, VGS minus Vt, right? So this is the first formula. What is the second formula? 2 IDC upon VGS minus Vt, that we are applying. Also you can apply the third formula, root 2 mu n Cx W by L into IDC. So all the values you are having, you can apply any formula. So this would be 256 micro divided by 1.6. 256 divided by 1.6. So 160 micro. We are getting 160 micro. Okay, I guess I calculated the GM value before as well, somewhere here, as far as I remember. Okay, forget it. So GM value is 160 micro. So what will be your V naught? V naught will be 166 micro into, okay, let's write it down in this manner, minus 160 into 10 to the power minus 6 into 25 into 10 to the power 3 into 6 into 0.658 Vs. So let's calculate this value. 160 into 25. 160 into 25 into 0.658, that is 2.6 into 10 to the power 3. So my answer would be 2.63. 2.63 minus. So this is my V naught by Vs. So this is the small signal gain I am getting, that is minus of 2.63. Okay, and don't think the calculation are big. These calculations are not big. These kind of calculation are asked in the examination. Even tougher calculation will be asked. So you have to be ready with that, right? So these calculation are very easy actually. This is not pretty big. When I deal the gate PYQs, you will see there is tougher calculation involved. Okay, so you should be ready with the calculation. You should be able to deal with micro, kilo. So what is the best way? This is the best way. That micro 10 to the power minus 6, kilo 10 to the power 3. You just need to develop the habit of writing the micro and kilo in the same manner. Even with the milli would be 10 to the power minus 3. So develop the habit of that. There will be square root involved, there will be squares involved. So you should be comfortable with all those things. You should be comfortable with this problem. Let's just assume in some problem you have to calculate root of 10 to the power minus 3. What you will do? The best way is break it down into 10 to the power minus 2 into 10 to the power minus 1. This you know, this will be 10 to the power minus 1 and 10 to the power minus 1. So you just need to calculate 0.1 into root of 0.1. So what will be root of 0.1? 0.1 root into 0.1. So your answer would be 0.0316. So your answer would be 31.6 milli. So that's how you can make your calculation better, because I have seen a lot of aspirants getting confused in these kind of calculation. Just because of calculation, they lose their 2 or 3 marks. So that should not happen. When I teach device physics, that means when I teach EDC, I will take a lot of calculation in action. So I will tell you how to actually solve the problems in the examination, how to actually calculate in the examination by using the gate calculator. So that we will see when we study the device physics, when we study electronic devices. Okay, yeah. So I hope you are comfortable with this question. Everything is clear. Let's move on to the next problem. Yeah, so this is the next problem. So considering lambda equals to 0, that means considering r naught equals to infinity, you calculated the gain to be minus 4. So when you consider lambda is 0, your gain was minus 4. Then later on, after that, you realize that your lambda is not 0, but it is 0.0625 volt inverse. That is the unit. So your lambda value was 0.0625. Then what is the actual small signal gain? Did you understand the question? First you thought that your lambda is 0. Then what should be the gain? If your lambda is 0, then simply the gain would be minus gm into RL. Minus gm into RL. That value came out to be minus 4. So what is the value of gm? 4 by 25k. So what is 4 by 25? That is 0.8, no? 4 by 25. Oh, it is 0.16, yeah. So it is 0.16 milli. So this is the value of gm that came out to be. Now later you realize that your lambda is 0.0625. That means there will be an r naught coming in action. If lambda is not equals to 0, that means r naught is not infinity. So this r naught will come in action. So now what will be your gain? Actual gain. What is your actual gain now? That is minus gm into r naught parallel with 25 kilo. Right? Because r naught will come in parallel to 25 kilo. So this is your actual gain. You have the value of gm. Yeah, I have the value of gm. You have the value of r naught as well. Sorry, you have the value of 20 kilo to 25 kilo as well, but you don't know the value of r naught. So from where will you calculate the value of r naught? Let's call it equation 1. So you need to calculate the value of r naught. We only know the one formula for r naught. What is that formula? If you remember the device physics lecture, what is that formula? 1 upon lambda id, right? And what is that id? Id sat but ideal. So you need to have the id saturation, id sat, since this is working in saturation region only, since okay, is it given it is working in saturation region, you have to consider this is working in saturation region because you are calculating the gain, so you have to consider it is working in saturation region. They should be given in the question. Even if it is not given, you have to consider it. So you just need to determine the value of id, that's it. Your R naught is 1 upon lambda id sat ideal case, in case of ideal current. So what is that current? id sat, that you need to determine. That's it. So from where can you determine that id sat current? Tell me. By the value of Gm. So what was the value of Gm you calculated? 0.16 millisiemens. From here you can calculate 2 into root mu n CX W by L. Mu n CX W by L is 100 micro into id. Since we are taking the same value in all the questions, so id value will come out to be 128 micro here, right? How did I calculate so fast? Because we have seen this calculation before in the previous question here, as I guess in the first question only. Here we have seen the same calculation. So IDC value will be 128 micro ampere. This is the ID value, IDC value or ID value. So from here, what will be your R naught? R naught will be 1 upon lambda. Lambda is 0.0625 into 128 micro. 0.0625. So 0.0625 into 128. That is 8. So basically your R naught is 10 to the power 6 by 8. If I need to write it in kilo, so what I need to do? 1000 by 8, right? 1000 by 8. 125 kilo. This would be 125 kilo. My R naught would be 125 kilo. Right? So this is what I needed to calculate. Now I can write my gain. So what will be my actual gain? That is minus Gm, that is minus 0.6 milli, right? Minus 0.6 milli. I will write 10 to the power minus 3 into 125 parallel with 25. 125 parallel with 125. These are in kilo, so I will write 10 to the power 3. 125 parallel with 25. So 125 into 25 divided by 150. That is 20.833 into 0.6 into 0.16. That is 3.33. So minus 3.33 is your actual gain. So this is your final answer. So previously your gain was 4, minus 4. Here your gain was minus 4. Then you realize that your lambda is not 0. Your lambda is 0.0625. Then you calculated the gain. So first, what was your gain? Minus Gm into RL. So the gain came out to be, and so gain was given, that was minus 4. From there you could calculate the value of Gm, that is 0.16. Now what did you see? That there is R naught involved, so your gain would be this. But you don't know the value of R naught, so you calculated the value of R naught. R naught would be 1 by lambda ID set, ideal case, in case of ideal. So Gm is this 0.16 millisiemens. So from here you could calculate the value of ID. Now people can have doubt, sir, if lambda is equals to 0, then there is, if lambda is equals to 0, then this is the Gm. This Gm is for lambda equals to 0. If lambda is 0.0625, then the Gm can change. This doubt many people can have. Yeah, this will change. Why it will change? Certainly it will change. Let's check that out. What I mean to say is that, sir, when lambda was 0, then you said your Gm is 0.06, sorry, 0.16 millisiemens. But if your lambda is 0.0625, then what will be your Gm? It can change, no? It can change, but while doing the AC analysis in the complete MOS amplifier, we will not change it. Whether it is lambda equals to 0 or lambda equals to any value, we take the Gm to be the same. What is the scene? What is our ID? ID is mu n Cx W by 2L VGS minus VT whole square. This is the case when lambda is equals to 0. If lambda is not equals to 0, this is the scene. So what will be the GM? GM is del ID upon del VGS. Del ID upon del VGS. So mu n COX W by L VGS minus VT square. So this GM is corresponding to this lambda equals to 0. And if I do 1 plus lambda VDS as well, because we are differentiating with respect to VGS, so 1 plus lambda VDS will be acting as a constant. So this complete expression is with respect to this. Now you will say that sir, lambda is very small and VDS is also small. Why VDS is small? No, VDS is not small. We are actually working in saturation region, so VDS is not small. So this complete factor is actually very, very small. So we don't consider it. Are you getting this point? This complete factor is very, very small. So usually we ignore this factor and say that GM is the same for lambda equals to 0 or some value of lambda. Let's assume if lambda was some 4, which will not happen. If that happens, then you need to take this in action. If lambda was 4, then you need to take in action because this value will be something good now. But if lambda is that much small, then what we usually consider that for lambda equals to 0 or lambda not equals to 0, every time the GM will be same. Although the GM is not same, the formula of GM for lambda equals to 0 is this. And the formula of GM for lambda not equals to 0 is this. Yeah, the formula is different, the value of GM would be different, but very minute. So we take the same GM value. So people can have this doubt, so I already cleared it. Are you getting this point? So 99.99% chances is there that your GM will not change. 99.99% I am saying. In some case, if lambda value is given very large, then you can consider something. In that case, what will happen? They will give you the value of VDS as well. What is this VDS? Large signal VDS. This is not small signal. All these are large signal. Everything, these are large signal. Everything is large signal. This ID is large signal. Everything is large signal. This R0 is a DC parameter. From DC you are calculating this. 1 upon lambda. Lambda value is constant. ID set. This is large signal. This is DC. So everything is large signal here. This is also large signal. Everything is large signal. So they will give you the large signal VDS value. Or you need to calculate somehow. How will you calculate? By using the circuitry. But here they have drawn the small signal model. So you can't calculate VDS value anyhow. Can you calculate VDS value here? By using this circuit, can you calculate the VDS value? Large signal VDS value? No. Because you don't even know what is the supply VDD here. Because they have already drawn the DC model only. Sorry, AC model only. They have drawn the AC model only. But for calculating the VDS value, you need the DC model. So you don't have that. So you can't calculate the VDS value. So there is 0.01% chance that the GM value can change. And if that changes, you have the aptitude to get the GM value from there. Well and good. So if anyone was having this doubt, I cleared it. So I can write a note here. Usually we consider same GM value for both of the cases lambda equals to 0 and lambda not equals to 0. So what is the GM value for lambda equals to 0? That is mu n COX W by L VGS minus VT whole square. And what is the value of GM for the case lambda not equals to 0? That is mu n COX W by L VGS minus VT whole square into 1 plus lambda VTS. So here I can write, since lambda is very small, we can take GM of lambda equals to 0 to equals to GM of not lambda equals to 0. Okay, so generally this is the case. Well and good. Let's move on to the next problem. So this is the next program, which is very interesting. So I need to see how much of you get the correct answer. So two circuits are given. For both of them, you need to determine the small signal voltage gain, and all the transistors are identical. This is M, this transistor is also M, this transistor is also M, this transistor is also M. So all the transistors are identical. You need to determine the small signal voltage gain. So try doing it on your own. Values are given mu n square W by L, Vt and all those things. So try doing it on your own. First tell me the gain of circuit A. What is your answer? The gain for circuit A, small signal voltage gain. We have already seen this diode connected load, right? Okay, there is some issue. Just a second. Just a second. Okay. I'm really sorry. I'm really sorry. This should be like this. I hope you did not waste your time. I'm really sorry for this. There are some people who might have wasted their time here. So both are NMOS. So we have seen the diode connected load, right? We have seen the diode connected load like this. So what should be the gain of first circuit? Now calculate the gain. What is the gain of first circuit? I have modified the circuit. The previous circuit was wrong. I have modified the circuit. What should be the gain of first stage? Lambda is equals to 0, so there is no R naught. So what is the gain? -1, right? What is the gain of this? -1? No. Why? Here the gain was -1 because the GM value for both of them was same. Why the GM value was same? Because both the transistor was having the same current. Upper one and lower one, both were having the same current. Here both are not having the same current. Here this 150 microampere current source is also there. So if M is having I current, then the upper one will be having I minus 150 ampere microampere current. Did you understand this point? So in the first one, both upper and lower transistor are having the same current, and both are identical. Mu and Cx W by L value is also same. So the value of Gm will be same for both of them, but the value of Gm will not be the same for in the case of B. So let's talk about the circuit A. So I will copy this circuit. So this was the best thing about this. If someone blindly does the small signal analysis, what people would have done, they would have blindly done the small signal analysis. They would have just open circuited it, and then they would have seen, okay, 1 by Gm from here and 1 by Gm from here. So both Gm are same, so your answer is -1. But that is wrong, right? Here both Gm are same because this is the current ID and this is also having the current ID. So let's call is upper and this call is lower. So both MU upper and ML will have same GM value. Why so? Because we know one formula of GM, that is root 2 mu n Cux W by L ID. Can you apply that formula 2 ID upon VGS minus VT? No, you cannot apply because you don't know the value of VGS here. You know the value of VGS here. What is the value of VGS? Here the value of VGS is 3. But do you know the value of VGS here? No, you only know this is 9. You don't know the value of this. Right? Are you getting this point? You don't know the value of this. So you only know the VGS here, that is 3. Yeah. So you cannot apply that formula. Also, you cannot apply the first formula, that is mu n Cx W by L VGS minus VT. Again, you don't know the value of VGS. But here you know everything. Here what do you know? 2 is constant. Mu n Cx W by L is same for both. Here I have written mu n Cx W by L is same for both. Here also, one thing also you know, that ID is same for both. ID, DC current is same for both. DC current is same for both. So GM will be same for both. So what will be the, what do you say? What will be the small signal gain? So you can draw the small signal model. So how will the small signal model look like? This we have already seen in the previous lecture, although. So both will be shorted. Both here will be shorted. This is V naught. We will only consider a small signal input now. Right? Yeah. So what will be the current here? GM GM V in. And what will be the current in the upper side? That would be GM V naught. So here you can say that GM V in is equals to minus GM V naught. So your V naught by V in would be minus 1. Let's take the second circuit, this one. So let's call this one as upper, this one as lower. So here, whatever the current is flowing here, I, this current is not the same. Let's call this current as I upper and this current as I lower. So I upper would be what? 150 micro minus I lower. Here the DC current is not same. Is not same in both transistors. So GM will be different. So how you can calculate the GM of both of them? You need to find the relation, right? You need to find the relation between both of the GM. So let's first find the value of IL. IL. What is the value of IL? That would be mu n CX W by 2L. I can directly write down the value. Mu n CX W by L is 100 micro. So mu n CX W by 100 micro. Mu n CX W by 2L. VGS. You know the value of VGS here. That is 3. Minus VT. VT is 1 square. Right? VT is 1. What did I do here? I am calculating the value of IL so that I could get to know the value of IU. I am calculating the value of IL so that I could get to know the value of IU. So I am calculating the value of IL, that would be 100 micro by 2 VGS minus VT whole square. So this is 4, so it would be 200 micro. So IL value is 200 micro. What will be the IU value now? So IL is 200 micro, so IU would be 50 micro, right? So if I am saying that GM corresponding to this is GMU and GM corresponding to this is GM corresponding to this is GML, GM lower, and GM corresponding to this is GMU. So what will be the relation between GML and GMU? What will be the relation? How you can determine it? You have two ways. First is that you can determine the value of GML as well, GMU as well, because you have the value of mu and CX WIL as well. You have the value of ID as well. So you can determine the value of GM. But better we determine the ratio, because in the answer we will be needing the ratio only. Because what is the small signal gain? What is the small signal gain here? What is the small signal gain? What is the small signal gain? That would be, the upper current would be GM U V naught, lower current would be GM L V naught, right? GM L V naught. So GML V in, sorry, GML V in. Lower current is GML V in, upper current is GMU V naught. So GMU V naught is equals to minus GML V in. So the gain would be GMU divided by GML. This would be the gain. Did I do the calculation right? V naught by GML divided by GMU actually. GMU V naught is equals to minus GML V in. So V naught by V in would be minus GML divided by GMU. This would be your V naught by V in. So minus GML divided by GMU. Minus GML divided by GMU. So you need to find the ratio, right? This calculation you can do. So eventually we need the ratio only. So what I see here is that, what is my GML? That is root 2 mu n COX W by L ID. This is a GM value. Neither GML, neither GMU. This is a GM value. For both of the transistor, MU and ML, for both of the transistor, mu and Cux W by L value is the same. The only difference is ID. So from here you can get to know that GM is proportional to root ID. Say yes or no. GM is proportional to root ID. Did you understand this point? For both of the transistor, mu and Cux W by L value is the same. The only difference is root ID. So GMU, what do I need to calculate? GML by GMU. So GML by GMU would be equals to root IDL divided by root IDU. So the current in lower one divided by the current in upper one, but the under root. So current in the upper one is 100 micro, 200 micro. And current in the lower one is 50 micro. So why is that negative sign is there? No negative sign. So GML divided by GMU is, what is that value? Root of 200 by 54. So root of 4 is 2. So GML divided by GMU is equals to 2. So what should be the gain now? That would be gain would be minus 2. That's it. Did you get this answer? Let's call this as equation 1, this as equation 2. So what was different here? Here both of the transistor was not having the same current. If both of the transistor were having the same current, then the GM value would have been the same, right? Root 2 mu and W by L root ID. Now both of them are having the different current. Then what was the task? You need to determine the current in both of them. One was having 200 microampere, other one was having 50 microampere. By this formula, we got to know that GM is proportional to root ID. Now no one will say that, sir, this was the formula. No, 2 ID upon VGS minus VT. Then you can say that, sir, GM is proportional to ID. If you say that, you are actually very unattentive. You are not listening to the lecture. Why it is wrong? Because you don't know the value of VGS. VGS is not constant. For this VGS is 3. For this VGS can be different. For the upper one, VGS value can be different. You only know the value of gate potential. You don't know the value of source potential. Here the VGS value is 3. Who knows the value of VGS is 6 here. So VGS value can be different here. So you can't say GM is proportional to ID. You only know one thing, that both of the transistors are having the same mu and Cux WIL value. So if both of the transistors are having the same mu and Cux WIL value, that means GM is proportional to root ID. That's for sure. That is done. GM is proportional to root ID. Then what was your gain? You could write the gain, because we have already seen this problem in the previous lecture only. So you could write the gain. Gain would be minus GML divided by GMU, right? So your target is to find the ratio between GML and GMU. Then you got to know GML by GMU would be root IDL by root IDU. So IDL value you have, IDU value you have. Both of the values you are having 200 micro divided by 50 micro and then under root. So that would be 2. So your gain would be minus 2. Did you understand this problem? This was very good problem, and this kind of question can certainly be asked in the written test as well and in the future upcoming gate examination as well. Understood? Well and good. So yeah, always while determining the gain, always while writing the gain, you need to consider the GM values. They can be different as well. So blindly don't go for the AC analysis. If you had gone for the AC analysis, what you would have done? You would have simply open circuited it. Then you would have short circuited this. Then you could see 1 by GM, 1 by GM, gain 1. That is wrong. You also need to consider that GM values. They can be different, right? Okay, well and good. Let's move on to the next question. This is the last one. Yeah, this is the last question of our this set of assignment. After that, we will be studying common gate and common drain amplifier. After that, we will be solving more assignment, 2 or 3 more assignments, because there will be a lot of problems. I picked only a few problems now. I have a lot of more problems. So that we will see in further assignments. So let's solve this problem. You need to determine the bias current in the transistor. Current in the transistor. So this current you need to determine. Let's call this current as ID. So what is that current? 100 microampere? No, that is not 100 microampere. It is sure that this current is 0 ampere. It is certainly sure. This is sure. But it can drive some current here as well, no? Right? So that 100 microampere current which is coming, that will be divided into this current that is going from 40 kilo ohm and this current ID. Are you getting this point? So that 100 microampere current which is coming, that will be divided into two parts, 40 kilo ohm and then ID. Well and good, understood? So let's call this potential as V. Then what will be this potential? This potential will be V by 2. What is the region of operation here? It is not given that it is working in saturation region. We can determine what is the value of VDS. So first we are calculating the bias current. So for calculating the bias current, you need to determine the region of operation. So first, what is the value of VDS? VDS is V. What is the value of VGS? That is V by 2. What will be V overdrive? V overdrive will be V by 2 minus 1. So here you can see that your VDS is greater than V overdrive. That means it is working in saturation region. Right? It is working in saturation region. So tell me, what is the current flowing here in this 40 kilo ohm resistance? In both 40 kilo ohm resistance, what is the amount of current flowing? What is the amount of DC current flowing? What is the amount of bias current flowing? V by 80 kilo ohm. Are you agreeing to this point? This potential is V. 40 kilo ohm and 40 kilo ohm both are in series because this MOS is driving 0 ampere current. So 40 and 40 both are in series. So V by 80 kilo ohm current is flowing. Are you getting this point? This is the potential V. Then there is 40 kilo ohm resistance. Then there is one more 40 kilo ohm resistance. And then this is having 0 ampere current. This is R, this is R. So what is the current here? V by 2R. That's the thing. V by 80K. V by 80K current is flowing. What is the value of ID now? What is the value of ID? So basically, the scene is 100 microampere is equals to V by 80K plus ID. So here there are two variables, V and ID. There are two variables which is not desirable. You need to eradicate one variable. So I can eradicate one variable. How? This is how I can eradicate one variable. So ID is equals to mu n CXW by 12, 100 micro by 2. VGS, what is the value of VGS? VGS is V by 2. VGS is V by 2 minus VT whole square. That's it. So this is how I can eradicate one variable. So this value I can put here. Now will it be a very tough calculation? Or is there any other way to determine the values? Because I think this will be a very tough calculation. Let's check it out. If it is tough, then we will find out some way. So yeah, let's check it out. So 100 micro is equals to V by 80K is there. So V by 80K is there, no? V by 80K. So 80K is there. So what I can do? I can write 0. What is 80K? 80K is 8 into 10 to the power 4. What if I write 0.08 into 10 to the power 6? Is that correct? Yeah, it is correct. So I am writing 0.08 into 10 to the power 6. That means micro. Did you understand it? What did I do here? V by 0.08 into 10 to the power 6. 10 to the power 6 went up, it would become 10 to the power minus 6. That would become micro. Right? Why I am doing so? So that I can cancel micro, micro and micro. Now what will come? My ID will come. So ID is 100 micro by 2. That means 50 micro into V by 2 minus 1 whole square. Micro and micro will get cancelled. So 100 is equals to, this will be 100 by 8. What is 100 by 8? 12.5. 12.5 V plus micro and micro are cancelled. This is 50. This bracket I can solve. A square plus V square minus 2AB. So it will be minus V only. This calculation is not tough. Okay, in the examination, these kind of calculation are asked. So you should be ready with that. Don't think that these kind of tough calculation will not be asked. 12.5 V square plus 50 minus 50V, right? So what I can do, 12.5 V square is there. This would be this, and this would be minus 37.5V, minus 37.5V, and this would make minus 50 is equals to 0. Well and good. Now I can divide 12.5. V square minus 3V minus 4. Very easy it became, right? It became very easy here. This is the final equation, V square minus 4V plus V minus 4. V value we are getting V minus 4, 1. So from here you are getting two values of V. V values are 2, minus 1 and 4. What will be the correct answer? You already know. This will be the correct one, because V cannot be negative. If V is negative, the transistor will be off. So V cannot be negative. V is 4. So your final answer is V is 4 volt. So if V is 4 volt, that means your VDS would be, VDS is 4 volt and VGS is 2 volt. VGS is 2 volt. So what did you need to determine? You need to determine the bias current in the transistor. So ID value would be mu(n) CoxW by 2L into VGS minus VT whole square, right? 100 micro by 2. What is VGS? VGS value is 2. 2 minus 1 whole square. So ID value came out to be 50 micro ampere. This is the ID value we are getting. That's it. Well and good. Now what is the next question? You need to determine the small signal resistance Rx. So try doing it on your own, then I will tell you how to determine it. So let's take this circuit and paste it here. Okay, I have to copy again. So this will be your small signal circuit, right? How it is the small signal circuit? This current source is gone. This will be open circuited. VDD is also gone. This is open circuited, and then this much circuit is remaining. So this is your small signal circuit, right? Small signal model. This is your small signal model. You need to determine Rx from here. So what we are doing? Small signal analysis. You need to determine Rx from here. That would be Vx, Ix. You need to determine Rx equals to Vx by Ix. So tell me, you can apply the nodal analysis. What is the current here? That would be Vx by 80 kilo ohm. What will be the current here? This is Vx, this potential will be Vx by 2. So the current here would be Gm Vx by 2, right? This potential is Vx, so this potential will be Vx by 2. So VGS is Vx by 2. So the current downward would be Gm Vx by 2. Vx by 80k, Gm Vx by 2 is equals to Ix. So this you need to calculate. Here what you can see, that is Vx by 80k plus Gm Vx by 2 is equals to Ix. So what will be your R out? What do you think? I am directly writing Rx. I hope you will be able to understand. My Rx would be 80k parallel with 2 by Gm. Are you guys able to understand it? How did I write it? 80k parallel with 2 by Gm. Vx by 80k plus Vx by 2 by Gm is equals to Ix. I told you V by R1 plus V by R2 is equals to I. So what will be the resistance? R1 parallel with R2, right? The resistance is R1 parallel with R2. So same thing is happening, 80k parallel with 2 by Gm. Now again you don't have the value of Gm. So you again need to calculate the value of Gm. So how will you calculate the value of Gm? You need to calculate Gm. Gm means good morning. Very bad joke. इस जोक के हिसाब से मैं कपिल शर्मा शो में तो जा ही सकता हूँ. Okay. So what is the value of Gm? That is 2 mu(n) CoxW by L ID. So you know that bias current in the transistor, that is 50 microampere. So root 2, you know the value of mu n CX double by L, that is 100 microampere. 100 micro into 50 micro. Your answer would be 100 into 100. So that would be 100 and micro will come out. So 100 micro. 100 micro. What is 100 micro? GM is 100 microsiemens. You can calculate this, you will get 100 microsiemens. GM is 100 microsiemens. So what will be your Rx now? Rx will be 80K parallel with 2 by 100 micro. 2 by 100 micro. 2 by 100 micro, right? Well and good. 2 by 100 micro. 100 micro means 10 to the power minus 4. 10 to the power minus 4. So it would go up. So it would become 80K parallel with 20K. That is your Rx. So 80 into 20, 16K. So what is the parallel combination of this? 16 kilo. Rx value you got is 16 kilo. Did you understand this? Small signal resistance we calculated. How did we calculate it? We just need to determine the value of Vx by Ix. So we have to anyhow get the value of Vx by Ix. That is our target. So we can apply nodal analysis. The current here was Vx by 80K. The current downward was Gm Vx by 2. So Vx by 80K plus Gm Vx by 2 is equals to Ix. So Vx by Ix, what will be the Rx? That would be 80K parallel with 2 by Gm. So you need to calculate the value of Gm. Gm you can get from the ID value root 2 mu x root mu n Cx double by L into ID. So mu n Cx double by L value you are having, that is 100 micro, and ID value you got, that was 50 microampere. So from there Gm value you got is 100 microsiemens, right? 100 microsiemens, that means here Rx value would be 80K parallel with 2 by 100 micro. 100 micro means 10 to the power minus 4. That means 20 kilo. So 80 parallel with 20 kilo, that would make 16 kilo. So Rx is 16 kilo. That's it. That's the final answer. So this was our assignment 6, which was the first assignment of common source amplifier. There will be more assignments, but before that we will study common drain and common gate amplifier. After that we can see another assignment. So I hope you are comfortable with the problem solving now. So yeah, these kind of calculation, these kind of questions can certainly come into your examination in near future. Well and good. So let's meet in the next lecture. Thank you.